Hello! Today we have an exciting topic called local linear approximation. So that's kind of just a fancy way of saying that we are going to be using a tangent line to approximate the value of the function at points that are close to the point of tangency. What that means in simpler terms is that if I know the equation of the line tangent, say, to this curve at when x is 2. So when x is 2, I know that point, and I know the equation of the line tangent at x equals 2. Well, then what if I wanted to figure out what the value of the point at 2.2 was? So right here. Or right before at, say, 1.9. Okay, how could I use that tangent line to approximate it? Well, and how would that tangent line's approximation reflect the actual value? Well, what do you notice about these points, these red dots that I put in, as far as where they are in relation to the tangent line? And hopefully you would say that they are beneath. And so any point on the tangent line that we are using to approximate would be an overestimate. And that's because this graph right here is concave down. Okay, so it's concave down, and any point on the tangent line would be an overestimate from what the actual value was. And we know it's concave down, of course, because the second derivative is less than 0. All right, so what would it look like then if I had a function that was concave up? So if I drew this and instead have a function that's concave up, okay, and again draw in a tangent line at a point. So this time I'll draw it in for this point right here. Draw in my tangent line. Okay, now what are we saying about that tangent line in relation to the points that are on the curve? Now we would say that any point on the tangent line, okay, is smaller than the value of the points on the actual function. And so we would say this would be an underestimate. And that's because this graph now is concave up. And of course we know that concavity comes from the second derivative, so it's concave up because the second derivative is positive. Okay, so we are going to use these tangent lines to approximate points that are close to the point of tangency, but we also have to recognize whether or not our estimate is going to be an overestimate or an underestimate. All right, so let's get started on trying a couple problems. Okay, this first example says the function f is twice differentiable with f of 3 is 2, f prime of 3 is 5, and f double prime of 3 as negative 4. What is the value of the approximation of f of 2.9 using the line tangent to the graph of f at x equals 3? So you can see 2.9 is obviously very close, a very close value to 3. All right, and we're given all of this critically important information about the graph, the function f at x equals 3. We're given the original function's value at 3, the first derivative, and the second derivative. And then they're asking, is this approximation greater than or less than the actual value of f of 2.9? That's where the overestimate or underestimate comes in. Okay, so let's first of all deal with the first part of it. We need to use the line tangent to the graph at x equals 3. Well, let's recall, if I want to write an equation of a line tangent to a graph, I need two things. I need the point of tangency, and I need the slope. Okay, so my point comes from the actual graph. And so this f of 3 equals 2 gives me a point of 3, 2. My slope comes, of course, from the first derivative. And so my slope here at 3 is 5. Okay, so now that I have those two things, I should be able to write the equation of my tangent line at 3, 2. So I would say y minus 2 equals 5, x minus 3. Okay, so now that I have that tangent line, I can go ahead and plug in 2.9 in for x. So f of 2.9 here, that's telling you that x is 2.9. And we are plugging that into our equation of our line tangent to the graph at x equals 3. and seeing what the value is. So we just go ahead and plug in 2.9 for x. Oops. All right, and so what we get there would be y minus 2 is equal to, I'm going to go ahead and do 2.9 minus 3 would be negative 0.1. So 5 times negative 0.1. Oh, what am I doing here? All right, which then, of course, is y minus 2 equals negative 0.5. Add the 2 over, so y is equal to 1.5. Okay, so the question is now, this would be my approximation. It's approximately, so y is approximately 1.5. Okay, so now that I have that, I have to think about the second part of the question. Is this approximation greater than or less than the actual value of f of 2.9? Give a reason for your answer. Well, in order to answer that, I have to think about the concavity of the graph, of the function. And that's where this second piece, the second derivative, comes in. Because my second derivative is negative 4, I know that this function is concave down. So I'm looking at a function that is concave down at x equals 3. So if this is 3, okay, and I were to draw on my line of tangency, all right, I would clearly be able to see that any point on this line is going to be greater than any point on this curve. And so since this came from 1.5 came from a point on this line, since I used my tangent line, the equation of the tangent line, to come up with this approximation, it is going to be greater than any value on this curve. It's going to be an overestimate. So I would go ahead and say that, let's see here, f of 2.9, which was approximately 1.5, is greater than f of 2.9, the actual f of 2.9. All right, and the reason for that is because my second derivative was less than 0, making the graph concave down. All right, so that's exactly what you would need to write, that the approximation was greater than the actual value, and that's because the second derivative was negative. Okay, the second example says y equals f of x. Let y equals f of x be a particular solution to the differential equation dy dx equals xy squared, with f of 1 equaling negative 2. Write an equation for the line tangent to the graph of of y equals f of x at x equals 1. All right, so the first thing they're asking us to do is write that equation, the line tangent to the graph at x equals 1. So we want to kind of look at what did they give us, because we know in order to write the line tangent, the equation of the line tangent, we need a point and we need our slope. Okay, so look at what they give us. They give us here that f of 1 is negative 2. So that's enough for our point. So 1, negative 2 is a point on the graph. Okay, they don't give us f prime, but in fact they do give us dy dx. So dy dx is, of course, what we know is slope. All right, so the derivative of the function is xy squared, which tells me that if I take my x and my y, I should be able to plug that in and find the slope. So dy dx is equal to x is 1 times y squared, so times negative 2 squared. So that would be 4. So my slope is 4 and my point is 1, negative 2, and so I'm able to write the equation as y plus 2 equals 4x minus 1. Okay, so that's part A. Part B says use this line from part A to approximate f of 1.1. All right, so that means I'm going to go ahead and take that, and I recognize that what they're giving me in here is my x value. So y plus 2 is equal to 4 times 1.1 minus 1. All right, so y plus 2 is equal to, see, this is going to be 0.1 times 4 is 0.4. Subtract the 2, so y is equal to negative 1.6. And remember, that's an approximation. Okay, is this greater than or less than f of 1.1? Explain your reasoning. Okay, so remember we said in order to determine if it was greater than or less than, we have to look at the concavity. And where does the concavity come from? The second derivative. Well, they don't give me information about the second derivative, but they do give me the first derivative. So if I want to take and find the second derivative at x equals 1, at this point, x equals 1, y equals -2, I need to go ahead and use the first derivative and take its derivative. So d2y over dx squared is going to be, all right, well, y squared, I have to use implicit differentiation. And so I would go ahead and product rule here would be first times derivative of the second would be 2y dy dx plus second is y squared times the derivative of first is just 1. Okay, so as I clean this up here, whoops, I would say that the second derivative is equal to, well, this here would just be 2xy. And then dy dx, remember, is up here. It was given to us as xy squared. So I'm going to replace this with xy squared plus y squared. All right, so at this point, I'm ready to go ahead and calculate what is the second derivative. I guess I could make this one step further if I wanted to, and that would be 2x squared y cubed plus y squared. Okay, so I can go ahead and plug in my x and my y that was given to me. All right, so that would be my x, of course, is 1. So 2 times 1 times -2 cubed is -8 plus -2 squared is 4. Okay, so that's going to be -16 plus 4 is obviously -12. So our second derivative here is a negative value, and so that tells me that my graph is in fact concave down. Okay, so I have a graph that is concave down, and its tangent line, if I were to draw the line tangent to it at any point, okay, that tangent line is going to be over the function, and that means it's going to be an overestimate. So if I were to make a conclusion, I would say that f of 1.1, all right, which was approximately -1.6, is greater than the actual value of f of 1.1. All right, and that's because the second derivative was less than 0, making it concave down. Okay, third example, let h be a function that is twice differentiable for all real numbers. The table above gives values of h at selected points on the closed interval -1 to 10. Suppose the second derivative is negative for all real numbers. Use the line tangent to the graph of h at x equals 7 to show that h of 8 is less than 5. All right, so they're telling us specifically to look when x is 7. So we have these three values here. We know that when x is 7, that h of 7 is 6, and that h prime of 7 is -1. So remember, if I'm asked to write the equation of the tangent line, I need two things. I need a point, and I need the slope. All right, well, both of those things are given to me in this table. I am told that h of 7 is 6, and I'm told that h prime of 7 is -1. So here's my point, all right, which would be 7 comma 6, and my slope here is -1. So I should be able to write the equation of the line tangent as y minus 6 is equal to -1 x minus 7. Now, they specifically want me to use that line to show that h of 8 is less than 5. All right, well, I'm going to go ahead and plug in the 8. The x value that they're asking me to approximate here, okay, that they're asking me to prove is less than 5, is 8. So that's my x value. So y minus 6 is equal to -1, 8 minus 7. So that's just y minus 6 is equal to -1 times 1 is just -1. Add the 6 over and I get y is equal to 5. Okay, so what this is saying is that on that tangent line, when I plug an 8 in, I get 5. Well, then why is it telling me to show that h of 8 is less than 5? Well, keep in mind, okay, this value was the approximation, which came from the tangent line. Is that tangent line an overestimate or an underestimate? That's where this information about the second derivative comes in. Once again, we have a second derivative that is negative. It says it right here. So if the second derivative is negative, we once again have a downward facing, and so our tangent line that's drawn in is an overestimate. Therefore, this is going to be our estimate that we got from the tangent line is going to be greater than the actual value. So that tells me that if this is greater, that h of 8 must be smaller. So we can go ahead and just make the conclusion that h of 8 is in fact less than 5 because h double prime was less than 0. Okay, last example says at the beginning of 2011, a landfill contained 1,000 tons of solid waste. The increasing function W models the total amount of solid waste stored in the landfill. Planners estimate that W will satisfy the differential equation dW dt equals 1/20th W minus 600 for the next 30 years. W is measured in tons and T is measured in years from the start of 2011. All right, a lot of information. Use the line tangent to the graph of W at T equals 0 to approximate the amount of solid waste that the landfill contains at the end of the first 4 months of 2011. All right, so if I'm asked to use this line of tangency, sounds like I first have to write the equation of the line tangent. So what do I need? Two things. I need a point. And of course I need my slope. All right, so if you look here, I'm not using x and y, so what are my variables? What is my independent and my dependent variable? So if I just even look at this, dw dt, okay, I know that that normally says dy dt. So my y is w and my x is t. All right, so this is instead of x and y, we're talking about t and w. All right, so they wanted us to write the line tangent to the graph of W at T equals 0. So I know that my time is 0. All right, and what is the W? What is the amount of landfill when time is 0? Well, remember, when time is 0, that's 2011 actually. And so if you read this very first sentence, it says, at the beginning of 2011, landfill contained 1,000 tons of solid waste. So the amount of waste in year 0, which is 2011, is 1,000. So that's my y value, if you will, of that point. Okay, now I need the slope. Well, where's the slope going to come from? Slope is going to come from dw dt. Okay, so I'm going to take that slope formula and I'm going to go ahead and plug in my t and my w. So that's this formula right here. So 1/20th times 1,000 minus 600. So my slope here is 1/20th of 400. Okay, your 0 would cancel. 40 divided by 2 is 20. Okay, so my slope is 20, and my point here is 0, 1,000. Okay, so when I write the equation of the tangent line, I want to be careful to use my new variables. So instead of y, I'm going to say w minus 1,000 is equal to the slope, which was 20, and then instead of x, I'm going to say t minus 0, which is just t. All right, so now I have to use that line to approximate the amount of solid waste that the landfill contains at the end of the first 4 months, which they say is when time is 1/3. So I'm going to go ahead and put 1/3 in for t. So that would be w minus 1,000 equals 20 times 1/3. All right, so that would be w minus 1,000 is just equal to 20/3. I'm going to add 1,000 over, which would be like adding, so I'm going to add 1,000, but it's like adding 3,000 thirds. So W would just be 3,020 thirds. Okay, and what does that stand for? Well, that was the amount of waste in tons. So we have 3,020 thirds tons of waste. All right. Okay, Part B of this question says find the second derivative, basically d2w over d2 squared, in terms of w. Use that to determine whether the answer in part A is an underestimate or an overestimate for the amount of solid waste that the landfill contains at time t equals 1/3. So we're finding the second derivative, and of course that whether that second derivative is positive or negative at that point is going to communicate to us about the concavity, which is going to tell us the under or overestimate. All right, so if I take the derivative of the derivative here, okay, so 1/20 is just a constant, copy that down. The derivative of w minus 600 is simply 1 dw dt. So I would just say dw dt. All right, so now, though, I'm going to clean that up by replacing dw dt with what it's equal to. So I'm going to put that in for this. So I have 1/20 of 1/20 w minus 600. So that is the second derivative. All right, now I'm ready to go ahead and plug in the point that I know. All right, and remember this is my t and this is my w. And so I'm going to go ahead and plug that in, plugging 1,000 in for w. So I have the second derivative is equal to 1/20 of 1/20 of 1,000 minus 600. Okay, so obviously this is 400. A 20th of 400 we said was 20. And so 1/20 of 20 is simply equal to 1, which is clearly a positive number. So now if our second derivative is positive, we know we're talking about a graph that's concave up. If I were to graph in my tangent line onto a graph that's concave up, I can see that it is clearly under the function, and so therefore our answer from part A is an underestimate. So we're going to say the amount of tons of waste that we found, which was 3,023 tons of waste, was an underestimate and that's because our second derivative is greater than 0. All right, so that concludes this question and also concludes this lesson. So the main idea that you want to make sure that you take away is that if we have a function that is concave up, which of course comes from the second derivative being positive, then any point on the tangent line is going to be an underestimate. If you have a function that is concave down, because the second derivative is negative, then any point on that tangent line is going to be an overestimate of the actual value. Okay, see you in class next time. Have a great day.